Good morning, students. So in this class, we'll be going to study about the EMF equation of DC generator, and also we'll be going to study about the different types of excitations of DC generators. So the first topic we'll be going to cover about the EMF equation of DC generator. So in order to find the EMF equation of DC generator, we have to first know some of the terms what will be denoting for the number of poles, the number of conductors, parallel path, etc. So let us consider P as the number of poles, main poles, not interpoles. It is the number of main poles. And we will be considering Z, capital Z, as the total number of armature conductors. Total number of armature conductors. And let us assume that capital A is the number of parallel path. Capital A is the number of parallel path and N is the speed of the armature in RPM, revolutions per minute. And phi is the flux per pole in Weber. Okay. So these are the different assumptions or different denoting factors we have to consider for finding the EMF equation in a DC generator. So EG, E suffix G is will be denoting for the generated EMF in a DC generator. So first of all, we have to find, I will show you, so these all things we already mentioned. So first of all, we have to know some of the things that I will describe here. So that is all about what we will be representing or how we will be finding as per the Faraday's law, how we will be finding the EMF equation. We already know that Faraday states that whenever there is a change in flux, an EMF is induced in the coil, right? The magnitude of induced EMF is given by the Lenz's law, and Lenz's law states that the magnitude of induced EMF is so as to oppose the cause produced in it, right? So as per the Faraday's law, E is equal to, we can write the equation for E, EMF E is equal to N into d phi by dt, right? If N is the number of turns and if we are considering the EMF per turn, ഒരു ടേണിലെ മാത്രമാണ് വൺ കണ്ടക്ടർ ഒരു ടേണിലെ ഇ എം എഫ് ആണ് കണ്ടുപിടിക്കുന്നതെങ്കിൽ ദ ഇ എം എഫ് ഇക്വേഷൻ ആസ് പെർ ഫാരഡേസ് ലോ ഈസ് ഈക്വൽ ടു ഡി ഫൈ ബൈ ഡി ടി where d phi is the change in flux and dt is the time difference in time. So change in flux with respect to time will be equal to d phi by dt will be proportional to EMF, right? And the direction for this induced EMF is given by Lenz's law, and Lenz's law states that the direction of induced EMF is so as to oppose the cause produced in it, right? The cause produced is the change in flux. So opposite to the direction of change in flux, the EMF will be producing, right? So we will be getting the EMF in such a way that it will be opposing the change in flux, right? So we also want to find the generated EMF. We are going to find the generated EMF in a DC machine, and here you can see we will be first finding the EMF generated in one conductor, and if there is n number of conductors, what will be the EMF generated? Likewise, we are finding. So first of all, we will be finding the EMF generated in one conductor. Okay. So we already know that during one revolution of an armature in a pole, if we are considering the pole as P, capital P, then each conductor will be cutting the magnetic flux P times, right? There will be Z number of conductors and each conductor will be cutting the magnetic flux P times. P is the number of poles. So what will be the flux cut by one conductor in one revolution? If phi is the flux and P is the number of poles, then flux cut by one conductor in one revolution will be equal to phi into P Webers. Weber is the unit of flux. Okay. Then, so we got the flux equation d phi as phi P. What next we have to find? dt, right? If we got both, we can divide and find the EMF equation. That is the procedure what we are doing. EMF per conductor we will be finding, and then we will be finding the EMF for n number of conductors. So we got the d phi value as p phi, right? Then we have to find dt. What is dt? time for one revolution. We are finding for one conductor, no? So the time for one revolution will be equal to 60 by n. If n is the speed, then 60 by n is the time taken for one revolution per second. Okay. So average EMF, we'll already know d phi by dt. We will substitute d phi as p phi and dt as 60 by n. So what we will be getting? 60 by n. What we will be getting? N will be going upside. So the equation will be becoming 5 p n divided by 60. That is what we got here. And this is for one conductor. Average EMF induced in one conductor. So what we need to find? We need to find EMF generated is nothing but it is the average EMF per conductor into number of conductors in each parallel path. So we know that if Z is the number of conductors and if Z is the number of conductors and A is the number of parallel path, then EMF generated is equal to average EMF divided by conductor into number of conductors in each parallel path. So we'll be substituting, we'll be getting it as 5pn by 60 into Z is the number of conductors, A is the parallel path, Z by A. So the final equation will be getting it as Eg is equal to 5Zn by 60 into P by A. This is the EMF equation. This is a very important equation and this derivation will be asking for the exam. Thank you.